Today we're going to talk about how we can go about drawing likelihood contours to show the errors in a measurement you make and also how these errors are correlated with each other. So suppose you've made a measurement of a number of variables and suppose they're grouped into a vector x, which you can say as components x1, x2, x3, and so on. So up to xn for n numbers that you've measured. Now, any realistic measurement is not going to have measured any of these numbers perfectly, and you're going to have some kind of error to it. And we can quantify this error using an error covariance matrix, and that's defined as the ensemble average of our measurements minus what I'm going to call x true, the true values, the values we would have measured if we had a perfect measurement, and this deviation x minus x true, if we take its outer product, an ensemble average, that's the error covariance. Okay. Now, without loss of generality, I am going to assume that x true is 0. In other words, I can choose my coordinates, I can recenter my coordinates so that the true value that I'm trying to measure is 0. And that's nothing magical, just for a bit of notational convenience here for me. And in that case, the covariance matrix is just the outer product of x with itself. And just, again, to be absolutely clear, to go from here to here, all I've done is to say that I'm choosing to center my coordinates so that x true is equal to 0. Now, to make this a little more concrete, if I sketch out a possible form for this matrix, the diagonal element of this covariance matrix is essentially just a spread in this x1 variable. And so that's what we would usually call the variance, right? It's called sigma 1 squared, the error of this x1 measurement. And similarly, the second diagonal element is like a measure of the error in the second variable x2, and so on down the diagonal. What the off-diagonal elements quantify, say I call this guy gamma 1, 2, and this guy gamma 1, 3, and so on, is it relates the errors between, say, measurement x1 and x2. Okay? Gamma 1, 2 tells me how correlated the errors are between x1 and x2. If x1 is high, does that imply that x2 should also be high? If it's low, does it imply that x2 is also low? So this error covariance matrix tells me not just the errors, but how correlated they are. More precisely, if I told you that the errors are Gaussian, then I can write down from my error covariance something called the likelihood function. Okay, so with this script L, this here is the likelihood function. And this is the probability distribution for measuring a particular set of values for x, what I'm trying to constrain. And if I tell you the Gaussian, then once you know the error covariance, you know everything there is to know about this distribution, and it's just given by a multivariate Gaussian distribution. Okay, so 1 over the square root of 2 pi to the n for n measured values, determinant of the error covariance down here. And with the Gaussian, the probability distribution is proportional to the e to the minus 1/2 X transpose sigma inverse, the inverse covariance matrix X. Okay, so it's a quadratic form in the exponent. And so, for example, if you look in the literature and you see that someone has made a Fisher information forecast for how well one can measure a bunch of parameters, they're in fact making this assumption of Gaussianity. Okay? And if you have knowledge that your measurement follows some other distribution, you can write that down for your likelihood function. But this is the more precise statement of what the error covariance means. It's telling you that with this error covariance, this is the probability distribution for what you've measured. Now, if I have n variables, this is an n-dimensional function, which can be hard to visualize. So one thing we can do instead is to think about the variables one at a time. Now that's a little tricky because these variables are correlated. If the error covariance is off diagonal elements, then errors in one thing I've measured are correlated to errors in another thing I measure. So in some sense, it's a little strange to ask ourselves, what the errors look like on a single parameter. But what we can do is we can do what we call a marginalization. And what I do when I marginalize over parameters is that I'm essentially saying I don't care about certain parameters. So suppose I were interested in just the likelihood of my first component, L of x1. Okay? And I can figure out the probability distribution for just this one variable by integrating this higher dimensional probability distribution over all the other variables, all the way from dxn, dxn minus 1, so on, all the way to dx2. Okay. Essentially, what I'm saying is that I know that my variables x2 through xn are also uncertain, so I'm just going to average over them weighted by this likelihood function, weighted by the probability of various values for these parameters, so that I end up with just a single probability distribution in one variable. And in our case, with the Gaussian distribution, to begin with, we end up with a Gaussian distribution afterwards. I should note, though, that if we didn't use a Gaussian to begin with, marginalizing over a bunch of variables doesn't guarantee that you get out the same distribution when you're done. And so that's great. With this Gaussian of this single variable, we have a likelihood function. It's just your usual Gaussian that you're used to. And so one way we can visualize this is we can draw this 1D probability distribution. Or another way we often do this is to draw, to plot our data. Say we measured it to be here, and plot an error bar about it to essentially capture the width of this distribution. Okay. Roughly speaking, the width of this guy is kind of this width. Now this is useful if I just want to know a single number. You've measured x1, what is the error on it? However, like we said earlier, this doesn't capture the correlation information. On the other hand, the full n-dimensional likelihood function is a little difficult to visualize. So one thing we can choose to do is to choose to marginalize over all but two of the variables. In particular, I can form a marginal probability distribution of two of my variables, which we compute by integrating the full likelihood function over all the variables except for the two that I'm interested in. So in this case, xn all the way down to x3. And then what I can do is that I can go and plot on a two-dimensional plane contours of this marginalized 2D likelihood function. And so, for example, here is an example set of likelihood contours from my research. Here are two parameters that you might be interested in measuring. And here I've shown two sets of contours, okay, that are both contours of constant likelihood in this two-dimensional plane. And immediately you see that these two variables are correlated. You see this orientation here of these ellipses. These guys are slanted up and to the right. If I measure a larger value for T virial, I'm likely to measure a larger value for the ionizing efficiency. Now, to be more precise, this inner contour has an area such that if the measurements were randomly drawn from this likelihood function, 68% of the time they would land within this first contour, and 95% of the time it lands within this larger contour. Okay. And for the rest of this video, we're essentially going to figure out how to draw these contours. Okay. How do we draw them such that we have one that encompasses 68% of the probability, one that encompasses 95% of the probability, or whatever probability you choose to compute, maybe 72%. Let's begin with some simple examples. So first, suppose we were to look at the single variable case. So we can think about this as either your measurement consisted of just measuring a single number, or you measured n numbers, but you've marginalized it down to a single one you care about. In our Gaussian case, we've got this likelihood function that looks like this, the likelihood of our single parameter x. And what we are asking ourselves is what region of this line in x encompasses 68% of the probability, 68% of the area under this curve. There are several ways to think about this problem. One way to formulate it is to ask ourselves, well, how far out from the central value of x, from my best fit value, from my maximum likelihood value, do I need to march out until I've encompassed 68% of the area? And to do that, you can numerically integrate out the Gaussian distribution. That's the likelihood here. Minus 1/2 x squared over sigma squared. And the answer turns out to be minus sigma on this end and plus sigma on the other end. So the 68% confidence region is your best fit value for x minus sigma and that value plus sigma. Another way to think about it is to ask ourselves the following. If I start out at the maximum likelihood value and I slowly march down looking at values of constant likelihood, how far down do I drop before I hit 68% area here? So that how far down do I drop, read off these values and get 68% of the area. Okay. And if you look at the form of a Gaussian, it essentially amounts to asking yourself what value of this exponent then do I have to get down to before I encompass 68% of the probability. And that's actually going to turn out to be the more useful way to look at the more advanced examples that we're about to do. For our second example, suppose we had two variables, but that they were uncorrelated. Two uncorrelated variables. Now, if my variables are uncorrelated, mathematically, that means that my error covariance is diagonal. Okay, the two variables don't talk to each other. They've got definitely have errors in the measurement so that they're on diagonal terms, but they're uncorrelated errors, so they're zeros for the off diagonal elements. And if I write out my likelihood function for this two variable case, again in two dimensions, the denominator here is just 1 over 2 pi determinant of sigma square rooted times e to the minus 1/2 x transpose inverse covariance x, like we talked about before. And if I actually write out this exponent here, just leaving out the constant factor for now, that's e to the minus 1/2 x1 squared over sigma 1 squared plus x2 squared over sigma 2 squared. So if we did what we did before, and we march down from the maximum likelihood point until our exponent here reaches a particular value, what we get here, you might notice, is the equation of an ellipse. So to say this again, perhaps in a different way, if I were to draw myself a parameter space plot, x1 and x2, if we go back to our equation, you notice that the maximum likelihood, the region where this likelihood function peaks, since it's a Gaussian centered at 0, is when x1 and x2 are both 0. So the maximum likelihood point is right here. And as we march down in values of constant likelihood, that's values of constant exponent there, which means that's where x1 squared over sigma 1 squared plus x2 squared over sigma 2 squared equals some constant. That is the equation for an ellipse. So I can actually draw these contours of constant likelihood like so. Here's one ellipse, and as I march down further my exponent, I get a different ellipse, broader one. And notice here that the normal axes for this ellipse are exactly the x1 and x2 axes, and that's because these variables are uncorrelated. And so what we can do now, if we wanted to, is just to go back and numerically integrate a Gaussian, which is easy in this case because the integral is separable, and you can do easily numerically the 1D Gaussians, and just figure out how far down, what constant value I need for this ellipse in order to encompass 68% of the area. Now, armed with this intuition, we can actually now tackle the more general case, where we have correlated variables. And just like before, where we asked ourselves how far down from the maximum likelihood we have to march to get to an area that encompasses 68% confidence, which as we said was equivalent to figuring out how far, what value our exponent had to hit. Here we can do the same thing for the higher dimensional, more generally correlated case and ask what value does this exponent have to hit before we encompass 68% of the likelihood, or whatever probability you choose. Mathematically then, we have the following problem. The exponent in our likelihood function is x transpose sigma inverse x, and we are trying to find the value of the exponent, this equal to some constant, such that when I integrate down to this value of the constant in the exponent, the area that I enclose encompasses 68% of the probability. Now, if I were to write out this equation here, for our two variable case, I get x1 squared sigma inverse is 1/1 component plus x2 squared sigma 2 plus x1 x2 sigma 1/2, or rather the 1/2 component of sigma inverse. And because sigma 1/2 is the same as sigma 2/1, the x2 x1 term is actually exactly the same. So I just had a 2 here, and this is equal to k. Now this is actually, again, an equation for an ellipse, only that with the x1 x2 term here, our ellipses are not going to be aligned with the axes we drew, but instead may have some kind of tilt to them to encode the fact that that the two variables that we're trying to measure here, x1 and x2, are correlated. So the question then is how far down from the maximum likelihood point we have to march, or rather how big of an ellipse we have to integrate over before the probability which is here the integral likelihood over these parameters over some area, say a little ellipse, is equal to some particular value, say 0.68 for the 68% confidence region. Now actually, if it weren't for just trying to understand where this comes from, there's actually a shortcut here, because this quantity here is actually the chi-squared statistic. So in principle, what you can do is to look up the chi-squared distribution for 2 degrees of freedom, since we've got two variables here, and actually just read off what the 68% probability region is, and that will give you the value of the k here. Okay? But what we're trying to do here is to try to understand where this comes from, so let's derive it from scratch. Now the reason this is difficult is because we're trying to integrate over a region with such a funny geometry. We're trying to integrate over some kind of slanted ellipse. What we can do to make our lives easier is we can do a coordinate transformation doing the integral not in x1, x2 space, but in some new variables z1 and z2, where this ellipse maps to a unit circle, which then makes the problem much easier, because then, for instance, I can do integrals in polar coordinates, which makes life easy for me. It's just a Gaussian integrated over a circular region, which I know how to do. Now, to actually find this transformation, I can use the following trick. So the error covariance matrix is what we call a positive definite matrix. It's only got positive eigenvalues, and that's necessary in order to ensure that no matter what basis you choose to express your measurement, you only ever get positive errors. You can't get negative variances, if you like. Can't say that the spread in my measurement is a negative value at best in an ideal world, I have a spread of 0. But one useful property of all positive definite matrices is that they can be written as the product of a lower triangular matrix and its transpose, okay, which is then going to be upper triangular. This decomposition is known as a Cholesky decomposition. And if sigma is LL transpose, and it implies that sigma inverse is equal to the L inverse transpose L inverse, and I can be sloppy about what I'm saying. This is the transpose of the inverse or the inverse of the transpose, because it turns out that those two are the same. You can prove that. So if I go back to my equation for my ellipse right here, I can rewrite this sigma in terms of my Cholesky decomposition. What I end up with is constant is equal to X transpose L inverse transpose L inverse X. Okay. So suppose I were at this point to just let this new variable z, which has two components z1 and z2, be defined as L inverse X, then you'll notice that this becomes Z transpose Z, writing it out in its components. This is Z1 squared plus Z2 squared. So if an equation K is equal to Z1 squared plus Z2 squared, this is a circle of radius root K. Okay. And so we've basically found our coordinate transformation that we need. It's not a unit circle like I said earlier, but that's easy. That's just a rescaling of the coordinates. The Cholesky decomposition provides us with precisely the right coordinate transformation that we need. So now let's actually perform this integral over this circle. And so we can say that the probability we want is equal to the integral of the circle over 1 over 2 pi square root of the determinant of sigma times e to the minus 1/2 X transpose sigma inverse X dx1 dx2. And I now have to change variables in this integral to my new coordinates, my z coordinates defined here. So let's do that. My integral is equal to this constant factor 1 over 2 pi square root of the determinant of sigma times the integral e to that exponent, which is now 1 minus 1/2 z transpose z. And with the change of variables, I need a Jacobian determinant, which is given by dx1, dz1, dx1, dz2, dx2, dz1, dx2, dz2. This is now an integral over dz1 and dz2. And to find these derivatives, I can go back to the coordinate transformation I wrote out earlier, which is that z is equal to L inverse x, and therefore I can actually write x as L z. If I were to write this out in components, what you see is x1 is equal to L11 z1 plus L12 z2 and so on for x2. And notice from this that, say, the derivative of dx1 with respect to dz1 is just L11. And so going back here, I have dx1 dz1 is equal to L11, dx1 dz2 is equal to L12. This determinant that you see that is needed right here is actually just the determinant of L. And so coming down here, you can rewrite this integral as the determinant of L over 2 pi square root determinant sigma integrated by e to the minus z transpose z dz1 dz2. Now let's simplify that integral a little bit. What we can recognize is the fact that the determinant of sigma we can write as the determinant of L transpose, which is the same as the determinant of L times the determinant of L transpose. And the determinant of a matrix is the same as the determinant of its transpose. So this just becomes the determinant of L squared. So if we now look back at our integral, we notice that this determinant L here exactly cancels out the square root of the determinant of sigma here. So the integral now, which we want to be equal to some probability p, say 0.68, is equal to 1 over the square root of 2 pi. We're integrating down to a circle of radius root k. V to the minus 1/2 z transpose z d2z. This is a 2D integral over a circular region, and so it makes sense to go into polar coordinates. And if we do so, we get this being equal to 1 over 2 pi, integrating from a radius of 0 to root k dz. This time the Jacobian is much simpler, 2 pi z e to the minus 1/2 z squared. That is an integral we can just do in our heads. This is equal to e to the minus z squared over 2 from root k to 0, which is equal to 1 minus e to the minus k over 2. So remember that this represented the probability enclosed by the circle of radius root k. So marching down from our maximum likelihood point, we need to get down to a radius of root k before we encompass a probability p. And so if I want to ask now our original question, how far down do I have to march down from the maximum likelihood point before I hit 68% probability, I can specify 0.68 on this side of the equation and solve for k. What we end up with then is that k is equal to minus 2 times the natural log of 1 minus p. Now, writing this back out, remember this is the radius of our circle, whose equation is equal to, it's given by K, Z transpose Z, which is equal to X transpose L inverse transpose L inverse X, transforming back to our original coordinates. And this, we just said, we need to have equal to minus 2 ln of times 1 minus p. So writing this out once again, this is essentially our final result. X transpose sigma inverse error covariance inverse X is equal to minus 2 ln of 1 minus p. Okay. And recall that this is an equation for an ellipse. So what that tells you is that if you have an error covariance sigma and you would like to draw the region in this correlated measurement space of x1 and x2 that encompasses a particular probability, simply insert that probability into this p here, and that's the equation of the ellipse that you need to draw. That is, for example, how I drew these ellipses right here. This first one was drawn by inserting p equals 0.68, 68% probability, and the second one was drawn for p equals 0.95, 95% probability. Now, that then is essentially the goal of this video, to figure out how to draw those error ellipses. But here's an interesting little fact that we can explore. So for two parameters, if I want p is equal to 0.68, turns out that I get, just plugging into our result, X transpose inverse X is equal to 2.3. Now for one parameter, back to our simple case that we did earlier in this video, if I again want p is equal to 0.68, well, the one-dimensional analog for this was x squared over sigma squared. That's equivalent to what I have here on this left-hand side. This is equal to 1 for 0.68. So essentially, what this is telling me is that as I go to a higher dimensional parameter space, I need to go out farther in radius, if you like, than I did for lower dimensions. Here's 1 versus 2.3. And the reason for that is because in 2 dimensions, to get my probability, I need to integrate over an area. In my parameter space. And so remember that these area integrals, suppose I were to transform back to my z coordinates where things are uncorrelated and the error ellipses become error circles, you pick up a Jacobian factor of 2 pi r dr. And this is for if I have 2 parameters. But if I have just a probability of a single parameter, I just integrate along a line. And so essentially the differential element is just dr. So the likelihood function in say 2D is weighted by r. So the parts of the likelihood far away from the origin, all other things being equal, are given a little more weight. Okay. And so this here, when we saw that we had to go out a little farther in the 2-dimensional parameter space than a 1-dimensional parameter space, was not an accident. As I go to higher and higher dimensions, the likelihood function far away from the origin gets weighted more heavily. So that's just a little bit of an extra interesting fact about integrating in n dimensions. But the summary of this video, the most important thing really, this equation here, which is all that we really need in order to plot these error ellipses. Now you know not just how to draw them, but where this equation comes from.